Good morning, my dear students. Welcome to the session on portal frame method. So, till now, earlier sessions, if you have followed, we have calculated starting from a column shear, then column end moments, and now beam end moments. So, this was the topic which is from the last session. Uh, so basically portal method has got two assumptions. So out of the two assumptions, first assumption is common for both the methods, like in case of either cantilever or portal, both are same. Okay, so only thing that is changing is the second assumption is very particular. So first assumption is same in both the methods. So when it comes to second assumption, so that you should be careful. So it's different for different methods. So like if you take portal method first, so how the uh, second assumption is. So it is like column shear for an internal column is twice that of the external column. That is the assumption. So we started calculating column shear. Okay. Once you complete the column shear, then the next connecting quantity is the column end moments. So step one is column shear. So you know how you calculate column shear. So by taking the section at the middle of each story and writing sigma fx0, then you will get the column shears. That's step one calculation. Okay. And step two is just by multiplying the column shear with half of the story height will give you column end moment value. So that is step two. Okay. So now step three also is covered in the last session. It is by taking joint moment equilibrium. So when you take a joint, you have both columns and beams joining there. So you know the column end moment. Okay. And you are required to calculate beam end moment. Okay. So by taking joint moment equilibrium, because joint as a whole should be in equilibrium, for joint that you are assuming to be rigid, if moments are different, they'll try to rotate the joint, so there won't be any differential rotation, so that the joint fails. So for that reason, the joint moment equilibrium is must. Okay, so we assume that joints are rigid. Hence, we say there is no differential rotation. So hence, no differential rotation means no bending moment. Bending moment should be zero. So what is the meaning of the differential rotation? Means what? Say if there is a beam and column joining at a joint, the rotation of column should be equal to rotation of beam. Okay, so together they should rotate the same angle. Means what? They should maintain 90 degrees, whatever may be the reason. So you load it with any load, the beam and column, the joining at a joint should, if they rotate, they should rotate by keeping that 90 degrees between them as it is. That is the meaning of uh, differential rotation is zero. Differential rotation means difference in rotation of the members joining at a joint. Okay, so if they maintain 90 degrees, we say that the difference in theta between these two is 0. Okay, so that 90 is maintained, there is no difference. Say when you say there is a differential rotation, say when you load some value on a beam or column, if say this is rotated by some 10 degrees and this is rotated by 20 degree, then the angle became 80. So what is the differential rotation now? It is this rotated 20 and this rotated only 10, so the differential value is 10 degrees. So there you can't say bending moment is 0 because there is theta. So when theta is present, there should be moment. Okay, so this is the reason why very clearly why we apply joint uh, uh, moment as 0 condition. Okay, so this how we take joint moment equilibrium. Right, let's go to the PowerPoint. So this was the last step calculation. The bending moments and all we have calculated by joint moment equilibrium. And we know the beam moments we have calculated, like topmost beam 20 and the uh, like 50 kilonewton meter for the second story beam and then 70 for the first story beam. So when it comes from bottom 1 2 3, this is how it is, right? So let's go to now step 4. So once you calculate beam end moment, okay, so what next you are able to calculate? So once you know the beam end moment, so imagine this is a beam and the beam is being made apart by the reason that at midpoint you have point of contraflexion, that's imaginary hinge. So I make the beam into two parts. Okay, so here is a hinge there. So you know the bending moment value. Let's say we have taken topmost beam. So this is the moment that is present. Same way here you have bending moment present. Okay, so shear, if you see that this should be the shear on this part, this should be the shear on this part. Reason behind this is anti-clockwise, so this direction is because of this shear force. Okay, and what is this one? This is half of the span. So for example, span AB is 6 meters, so half of that 3 meters. So this is 3 meters, this is also 3 meters. So this is shear force in AB, beam AB, because you don't have any gravity load to generate any shear. So only the end moment is the reason for development of shear. No gravity loads at all. See, if you see sum of all forces either to the left or to the right, there is no force at all. There are only moments. Okay, so that's the reason why. Shear will only depend on this bending moment that is already being developed. 20. Okay, so 20 this VAB into 3 is equal to that force into distance is moment here. You know the moment value and you know the span value, and you don't know V value. That's simple it is. Just force multiplied by this distance is equal to bending moment. So V into 3 is equal to 20. Okay, so V is then 20 by 3. So this is how it is. So moment is 20, bending moment is equal to force into half of the span. So 20 is equal to V into 6 by 2, that is 3 meters. So 20 by 3 6.667 kilonewtons is shear in AB. Same way to the other part of the beam also. You see, this is 20, this is 3, and this is V value. So V into 3 is equal to 20. Same, the direction should match with this. Okay, so there is a hinge in between, imaginary hinge there. Okay, so that's how the shear forms to the left of the section and to the right of the section. The shear is always not a single arrow. Representation is always shear in the sense there should have it should have two forces. To cut, to shear means what? To cut what you need. Okay, a single force cannot cut the beam. You need to have two uh, arrows. uh, Imagine two knives, like two knives to slice a particular member. Okay, so imagine you have a stick. So if you want to slice it, so you have to have two knives. Okay, so if you apply only single force, the beam will bend. It won't be cut. Okay, so if you have two forces, then just two forces will cut the member. That's why we call it as shear. So there should be two arrows for shear to represent. Anyhow, when you take an element, again we talk about strength of materials. Shear should exist with four arrows. Two are applied and two are the reciprocate action of the applied shear. Okay, we call them complementary shear. Right, it's all part of the subject. Okay, now we limit our discussion. So next beam, BC. Okay, AB leftmost beam, top story. You see, top story, leftmost beam, then middle beam, then the right hand beam. Right. So the span is 4 meters. So 4 by 2 will be 10. 20 by 2, 10. Same. CD span is 8. So 20 by 4 divided by 4 here. 20 divided by 4, 5. So maximum shear force is happening in the middle. That is 10. Okay. Similarly, the next uh, story, like second story beam, GH, EFG, and EF from left to the right. Left span 6 meters, middle span 4 meters, right hand span 8 meters. So maximum shear force in the middle 25. The middle beam, I mean to say, there are three beams in the sense floor, complete floor. If you say a continuous beam, top floor beam, middle floor beam, and the bottom floor beam, like that. So this, there are three beams which are continuous. Among them again, there are three independent beams like AB, BC, CD. Beam AD is a continuous beam. It consists of three spans, AB, BC, CD, right? That's how if you can call it. So HG, GF, and FE, the middle one. GH, FG, EF. Okay, so 25. Same way, the bottom, no, first story beam, I can call it. So 6, 4, 8 spans. So same, the maximum in the middle. If the span is less, shear is more. Okay. So very logical. Long spans, no, bending moment is predominant. Short spans, shear is predominant. Okay, it's all is a part of the knowledge that you have already studied. But anyhow, so this is how the shear force values in beams are calculated. Just with the beam end moment and by the span. Knowing the span, knowing the beam end moment, we are able to calculate the beam shears, and finally uh, putting it in the diagram. Answer representation is much important. So already there is a diagram with you representing step 1 answer column shear, step 2 answer column end moment, step 3 answer beam end moment. Now step 4 solution is complete. That you should represent like this. Middle of the beam, middle of the beam, the two arrows left upward, there should be left upward, right downward, all cases, all cases. And this is not fixed notation, right? All these notations have come because of this externally applied load directions. So they are acting towards right. So if that direction is changed to left, all these directions will simply reverse. In that case, we will get left arrow downward, then right arrow upward for shear. Likewise, everything now will simply uh, change the notation. So you must be careful in assessing the sign convention, how you put your sign there. Okay, right. So shear forces, you represent all shear forces that we found with the calculation just now, right? So these are the shear force values. So 35 is the maximum shear force, and that happens at the bottom story beam in the middle, okay, portion. JK beam JK is having maximum shear force. Okay, so this is how step 4 is to be completed, right? So always see the picture. The diagrammatic representation is must, and it should be very clear. No clumsy. Anywhere you see the diagram, how beautiful it is. You should represent it in such a manner to have full clarity for the one who sees it. Okay, right. Thank you.